We left off in the last video talking about interacting particles in the two-particle system. So if you remember previously, in the non-interacting case, that the potential energy, which is a function of the position of particle 1 and particle 2, we could break it up into potential energies of just the individual particles with no interaction term whatsoever. But right now what I want to talk about is the interacting case. How can we solve that? So again, we're going to restrict ourselves to just two particles. So what this means is that our potential energy function is not going to be equal to just the sum of the two potential energies. So let's consider one specific case. So I'll call this case B, where the potential energy now is the potential energy of the distance between the two particles. So what I mean by that is there are no external interactions. So there's no forces applied just to particle 1. So the only interaction is between the two. So we have these two particles, particle 1 and particle 2, drawn classically, and we can then look at the interaction of the distance between the two. So what we want to do is, we want to come up with an equation for Schrodinger's equation that is separable. Then it's much easier to solve Schrodinger's equation if we can break up these two coordinates. So the first coordinate we're going to use is, we'll just call it x, and that is the difference between the positions of the two. So it's the distance between the two particles. Now a second coordinate is the center of mass, where we take the mass of one particle times its position, the mass of the second particle times its position, divided by the total mass. Where in this case, the total mass, m, is just m1 plus m2. So essentially what we're doing is we're not losing any information, right? We start with two coordinates, x1 and x2, and we're just changing them into a more convenient coordinate system of what's called the relative position x and the center of mass position xcm. So we can also write another type of mass called the reduced mass, which is the product of the two masses divided by the total. So like I said, we're not losing any information going from two coordinates. We're going from two coordinates to two coordinates. We're just going to write them in a more convenient set of coordinates, and which we'll see in a minute how that helps us. If we look at the momentum, so the momentum of the center of mass is just the mass times the velocity of the center of mass, x dot. So now the whole system is moving, and we're tracking its center of mass position. So we can actually, this form reduces because if I take the derivative of the center of mass coordinate, then what I get is mass of 1 times x1 velocity, so the velocity of particle 1, times the mass of 2 times the velocity of particle 2, divided by its total mass. So the total masses cancel, and what we're left with is m1 velocity of 1 plus m2 the velocity of 2. So it's basically the sum of their momentum. For the reduced mass, for the reduced momentum, we get the reduced mass times the velocity of the reduced coordinate. Okay, so now we've got position, we've got momentum. We now have essentially the operators that we need to apply it to the problem. So what we can do is we can now rewrite the Hamiltonian. In classical mechanics, the Hamiltonian is a function of the center of mass and the reduced coordinates. And so it would be equal to PCM squared over 2 capital M plus P reduced squared over 2 reduced mass plus this potential energy, which is only dependent on the reduced position. Okay, so we need to quantize this. We need to change it over to a Hamiltonian for quantum mechanics. And what we get is essentially changing our coordinates into operators. So the Hamiltonian in quantum mechanics would just be the momentum of the center of mass, operator squared, divided by 2 capital M, plus the reduced momentum squared over 2 times the reduced mass. Again, these are operators, plus an operator for the potential energy, where now I'm using a capital X instead of a little x to show the operators. And these follow the commutation relations. These operators do. Like so. Okay. Okay, so in the end, what do we get if we apply this Hamiltonian to our two-particle state? And what you should get is a separable equation where the wave function of the total energy, which is a function of the center of mass position and the reduced position, and we should be able to get a separable set of wave and we'd be able to separate the wave functions. So we'll get one for the center of mass times the relative position, so E relative, like so. So we should be able to take that, plug it into our Hamiltonian, and we should be able to solve the Schrodinger equation. So I'm not going to necessarily go through that. I mean, we could. All we would do, well, why don't we go and do that? Why don't we go ahead and start just kind of writing it out? And so what you get is something like this, where now if we write in the Hamiltonian, we get minus h bar squared over 2 capital M, the derivative, the second derivative with respect to the center of mass, minus h bar squared over 2 mu, the second derivative with respect to the reduced position, plus the potential energy. All of that is now operating on our wave function, and that gives us the total energy times the wave function. So if we now put in our separated wave functions, and I'm just going to try and pull stuff together, what you would get is minus E relative times h bar squared over 2m, the second derivative for the wave function that is the center of mass, minus h bar squared over 2 mu, so all of this has to be multiplied by ECM plus the potential times those wave functions is equal to the total energy. Okay, so we can do the same thing now, where if we divide both sides by the product of those wave functions, what we would get is minus 1 over E relative h bar squared over 2 capital M sorry. Let me change this up. So this would be E center of mass, E center of mass, like so. So you get that term, and then I would also get a term minus 1 over E, 1 over the wave function, E relative, h bar squared over 2 mu, the derivative, second derivative of the wave function for the relative motion, plus V. So I've essentially written it as two terms, and then these two things added together are equal to the total energy. So therefore what we have is a Schrodinger's equation. So ECM is equal to minus 1 over the wave function for the center of mass and I get a Schrodinger's equation for the relative motion, where that's where the potential energy is contained. Right there. So essentially what we have is the total energy is made up of the center of mass energy plus the energy of the relative motion. And we now have two independent Schrodinger's equations, one for the center of mass and one for the relative motion, which we can then solve. You can solve for each of those wave functions, and you then have the solution to your problem. The interesting thing is the interaction is only in the relative motion, that the center of mass is essentially a free particle. So we could use that, we could use the solution that we already know for a free particle, you know, or you could just solve the equation. It's not that hard of a differential equation to solve. It's essentially sines and cosines. It's a propagating wave. And then to solve the relative motion, you need to know the form of the potential energy. But again, that's essentially the solution. The solution is that we have a sum of center of mass motion and of relative motion. Okay, so that pretty much, is the solution to the problem. And so we've looked at two different cases, non-interacting particles and interacting particles with a very specific potential energy, and that is relative, potential energy, the internal interaction between the two particles. Okay, so from there, we could, expand now the problems. You can go to n particles, and that kind of becomes very difficult. One particle is trivial, two particles can be solved exactly like I've shown right here, and three particles, that becomes very, very difficult. Essentially, there is no analytic solution yet for the three particle system. There's always has to be some approximations that are made. And then the other case is cases of n particles and m dimensions. And again, that becomes more difficult. So we'll save that for another time.